All right, this is the last section in this notes packet. It's called the whole to China problem. And the reason it's called that is because there's this question that College Board will sometimes ask, and it has been asked in the past on some past AP Physics C mechanics tests. But it's this idea that you have a planet, okay, perfectly spherical, and you drop a mass into the hole. So you have a hole that's cut through this planet of it's drilled right through, and it goes through the two poles. It's perfectly spherical. It has uniform density. Okay. If we drop an object into that hole, what'll happen is what's going to happen is it'll go down. It'll actually oscillate in here. Okay. That's kind of something new. Okay. That's not something that we ever really looked at in physics one. But it's kind of a weird thing to think about, but it does get asked a couple times. Okay. Okay. Expressions for the following: mass m sub r that is within the sphere of radius r. So this is an instant in where the object is a distance r from the center of the planet. So the center of the planet is, right here in the dead center, and this right here is actually like a sphere. It's kind of like a segment of the sphere, right? So basically what's happening is we're making a sphere that has the radius of this. Okay. Okay. Um, to find out how much mass is within that sphere, the most critical piece of information that you need to get from this is that there's uniform density. So that means that there's the same mass per volume throughout. So really what I can do is I can just write a ratio for the volumes and the masses, right? So if I know that in the sphere of radius big R, 4/3 pi, I'm doing a mass to volume ratio, okay? R cubed, okay? Oh, capital R, sorry, for the whole sphere, then it should be the same. It should be proportional to the amount of mass that's just within the sphere of radius little r. So I can set that equal to big M sub r over 4/3 pi little r cubed. Now, this is actually not that hard to solve because you've got 4/3 pi here, which cancels out with 4/3 pi on the right side too. Okay, you get capital M sub r over r cubed is what's left, and then you set that equal to capital M over capital R cubed. And what ends up happening is if you want to get M sub r by itself, okay, I multiply that by r sub 2, so this becomes little r cubed over capital R cubed, okay, times big M, okay. And this right here, this part right here, the r cubed over r cubed, this is the same as the ratio of volumes. Okay, because if you take the ratio of the volumes, 4/3 pi little r cubed over 4/3 pi big R cubed, you're going to see that the 4/3 pi cancel out on both of them, and you're left with exactly that. Okay. To find the gravitational force exerted on the object, all I got to do is use my gravitational force equation. Okay, F sub g equals negative g little m big M over r squared. Okay. When I do this, I actually have to use my radius. I'm actually going to use my radius little r. Now, I do need to make a substitution. Okay, that this big M should actually be big M sub r, and I need to substitute it for the expression I got earlier. So that's going to become negative g little m over r squared times r cubed over r, big R cubed times big M, mass of the planet, right? Well, then hopefully you notice that this r gets completely eliminated. One r remains in the top, and then when you multiply it, the big R takes the place in the bottom. So this really just becomes the force of gravity is equal to negative g little m big M over capital R cubed times little r. Okay? So it is going to look a little bit different than it did earlier, but that's all you got to do. You just have to find it with respect to that. Okay? Is the motion simple and harmonic? I can prove this to you. It is, and I'll tell you why. You can prove it with words. You can prove it with math, but you will have to do the math anyway. So we might as well show you both. Well, the force is opposite displacement. Force is opposite displacement. Okay, and the force is directly or is linearly proportional to displacement. We saw that earlier. The farther you go a distance little r, the more force is applied to it, and it's opposite displacement because if you're above the center of the Earth, what's actually going to happen is the object, so I don't remember if I explained this, but the object, when you drop it in the top, it's going to go down, it'll go past the center of the Earth, and then it'll actually bounce back up, and it'll oscillate, okay? So when you're right here, your force is pulling down, okay, because you're displaced above it, and then when you're at the bottom, your force is pointed up because you're displaced below the center of the Earth, okay? Okay. So what I'm going to do to prove the simple harmonic motion, and it's like a two-step derivation, is all I'm going to do is I'm going to say, ma equals negative g little m big M over r cubed times r. Okay. Well, guess what? Believe it or not, if I can cancel out my m's. Okay. And when I do that, this becomes, believe it or not, the simple harmonic motion differential equation. Okay? So this will become, A equals negative g little m big M over r cubed times the distance r. This is the simple harmonic motion differential equation because A is the second derivative of position. Okay? So this is going to be d squared r over dt squared equals negative omega squared times r, okay? And you can see how those all connect. So, yes, this is simple harmonic motion because it fits the equation, okay? To prove it, well, the expression for omega, all I got to do is just this right here. So I can drop the negatives and root both sides. So omega has to be equal to root g little m big M over r cubed, okay? And then I can set that equal to 2 pi over t. I flip both sides and multiply by 2 pi, and I end up getting t equals 2 pi root r cubed over g little m big M, okay? Oh, I'm so sorry. Why I don't know why I carried over the big M like throughout the whole thing, even though I literally just canceled it out. Okay, so just ignore that part. Okay, ignore the little m's. I messed up a little bit there. Okay. 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 So there's that, right? There's the period equation. Okay. Consider instead that the object is shot from just above the hole so that it makes a circular orbit that just skims the surface of the planet. So basically what this means is the radius of orbit is basically equivalent to the radius of the planet. Will it take more or less of the same amount of time to reach the other end of the hole? Well, if I recognize that the gravitational, this is a circular orbit, okay? So what I can do is I can do centripetal force. I can do g little m big M over r squared equals m omega squared times r. And what I can recognize is, again, my little m's cancel out. And if I divide the r on both sides, I will get omega squared equals gm over r cubed. Hey, wait a minute. That right there looks very similar to what I got here. So if I squared the omega, this would be gm over r cubed. Wait, that's the exact same thing. Okay? So the omega is the exact same thing as up here. So this means, okay, this is the same as above, okay? So this means that the period of the orbit is equal to, right, and the period of the simple harmonic motion are equal. So it should take the same amount of time to reach the other end of the hole because the periods are going to be the same. So if they're launched or dropped at the exact same time, they will reach the other end of the hole at the exact same time. Okay? Kind of cool to think about. Okay, that's it for simple harmonic motion and gravitation. Okay? All right, girl boss it up.